Hello, this is Guava Moment, and welcome to the SpaceChem Thunderdome, where 16 men enter and only 8 leave. We'll start off with Cannibal K9 versus Krackor. I'm going to be showing off the higher ranked person's solutions first when I do these head-to-head comparisons, so in this case I'm going to start with Cannibal K9. As I'll walk you through his solution, he starts off by separating out the acetylene from the input of these 3 different gases, methane, ethane, and acetylene. Acetylene's going to need the most work to turn it into methane, so he separates that out, leaving this with methane and ethane up here. Going to this reactor, splits the ethane into half, bonds it with a hydrogen so that he gets 2 outputs of methane from here. Blue works by feeding methane straight across, and then red works to prime the hydrogen down here so that the ethane halves can bond together and make methane. So this hydrogen, where does that come from? If you see, he's got the acetylene building up in this pipe. The acetylene will also need hydrogen, but we'll get back to that in a second. He has this reactor to take his input of hydrogen from here and split it on a 2-to-1 ratio. Blue outputs 2 hydrogens down for every 1 red hydrogen up. So that's 1 hydrogen going up into here, and 2 hydrogens going into this reactor with the acetylene. Let me just sit and watch this, see how this works to use the acetylene and hydrogens to build methane. So there, that's Cannibal K9's solution. I see no obvious logical flaws with it. Important things to know about production assignments is that these outputs, they spit out 1 output every 10 cycles. So if you want a fast time, you want to have no backlogs here. This is going to be your main bottleneck. As we look inside this reactor, we can see that the paths are pretty short, and since it's double pumped, you can have longer paths. The key is that he's not having a backlog here, so that everything is getting inputted and outputted pretty much right away. So the final score comes to 909 cycles. Krackor does something a little bit different. He starts off as well by having a special case for the acetylene and kicking it off to the other reactor. But when an acetylene shows up, which it will in a second, he leaves the hydrogen here. So down into this reactor on this side, the omega output, it's the methane, ethane, and another hydrogen. This reactor here takes all of that and sorts it. Hydrogen gets output in this 1 square here. Methane and ethane get split out up here. He does also the work of splitting the ethane in half right away. So both of these get fed into this reactor, where if it's a methane, it just gets fed across to one of the outputs. And if it's an ethane half, then it bonds with the 1 hydrogen and outputs. A series of flip-flops make sure that these are balanced, so it outputs 1 up and then 1 down for each Waldo. So that leaves the acetylene. There's a little different case here. Since it's just the carbon, it needs a bunch of hydrogen, so all of the hydrogen gets fed right into this. Then Krackor just does a thing where the carbon gets split, flip-flops around, bonds to the hydrogen, and outputs. Final time. 861 cycles. Krackor defeats Cannibal K9. So why is Krackor's solution so much faster? Let's zoom ahead to the end a little bit. The limiting factor in this solution is hydrogen. Look at all this carbon he's got built up here. He just doesn't have enough hydrogen to create a methane. So in Krackor's case, he's got, well, 5 hydrogen molecules here just waiting in the queue. If we go over to Cannibal K9's solution, near the end, he's got a whole bunch of acetylenes stuck here. Each one of these acetylenes has a hydrogen on it, so there's way more than 5 hydrogen molecules sitting here. That's why this one ends up slower. There's too much hydrogen trapped in this acetylene that's not being used efficiently. So, congratulations, Krackor. So now we know how to solve this challenge quickly. How do we solve it efficiently using minimum symbols? My first thought is, well, you need methane. There's a methane right here. Why not just take the methane and put it straight into the output somehow? And all the other stuff is just garbage. So the reason I made this challenge is because sometimes you just need miles and miles of buffer pipe. In this reactor here, both the ethane and the acetylene, which you don't need, have are 4 molecules or 4 atoms wide. In this case, red can grab them and drop them and output here into a huge garbage pipe. Eventually, there's a methane at some point. That gets dropped. Red doesn't pick it up, and it gets output to this reactor. This reactor is just a even splitter. So there's one output down, one output up. One output down, one output up. And then this reactor is also a splitter. The one issue with this, it's not that the world fills up with garbage in these pipes, it's that for every 1 methane that goes into this tank, and for every 1 methane that goes into this tank, 2 end up in this tank, because this splits in half, and this splits in half. So half of the methane in total goes in this top one, and then these 2 bottom outputs have to share the other half. It's a very, very efficient low symbol solution. I'm pretty sure 33 is the minimum solutions, or minimum symbols. But eventually this solves 57 cycles. Psuedodude. He has almost exactly the same thing. Note, it is also 33 symbols. He sorts his methane from his inputs the exact same way. He does something a little bit different with this first reactor, which I will get back to, and then this reactor is also just an even splitter, 1 up, 1 down. This guy, this is the thing. I'm not sure how this works totally or why this works. Psuedodude wrote me in an email, he said that he wrote a program to simulate this, and I don't know what happens. He says something weird happens at cycle 1300. Note at this point there are no methanes down here, not even a single one. But somewhere around here, red does a thing where now it finally syncs up properly and will actually grab most of the outputs. At this point, this reactor is an even splitter. It looks like it's 1 up, 1 down. Before cycle 1300, everything went down. He'll have to explain this to me, how he managed to figure this out or why this works. But at this point, everything's balanced. Now I don't want to miss this. It's kind of hard to zoom ahead. Okay, so he just needs 3 more. There's 1 up, 1 down. Look at this. This is the last methane he needs. There was no wasted methane, period. Somehow he found a way to split 1 stream into 3 like this, and I don't know how he did it. But to pretty much no one's surprise, Psuedodude wins based on the tiebreaker of least cycles on the low symbol solution. Congratulations, Psuedodude. Before we get to MrBlarney and Serbaldrig, I just want to show off my solution for the level Unbonding Gadolinium. The challenge in this level is without a bonder, find a way to remove 1 bond from gadolinium. That means at some point via a series of fusion and fission we need an atom with only 1 bond there. The 1 bond atoms are on the left side, hydrogen, lithium, sodium, all these guys, and fluorine. I made this one that works by splitting things down to fluorine. Works until that, using a flip-flop counter, do it until we get gadolinium oxide. Split the 1 oxygen down until it's hydrogen. Fuse that hydrogen into this oxygen, that makes fluorine, and then the cesium left over, fuse into that, makes gadolinium again. So that's one way of solving it, and you know what, it's Turned out pretty slow. So this was my solution, 818 cycles. Let's see some guys who put a lot more effort into this. MrBlarney was higher ranked, so we'll show his first. Starts off by splitting, dropping some stuff, leaving a bunch of garbage all over the place. What is he doing? Okay, so you see all this stuff over here. And this helium. All garbage! All this, all garbage. This neon, that's what's important. So let's see what happens. Fuse neon into gadolinium, makes tungsten. Split tungsten once to rubidium, which only has one bond. So he's got his one bond now. Fuse argon into that, split potassium. Hey, there's his neon again. And his single gadolinium output. So what MrBlarney has done, he's used neon as a catalyst. Again, there's another catalyst solution that I never thought I would see. I never really thought that you would find a legitimate use for a catalyst in a non-gimmick challenge like that's not specifically catalyst challenges. So that is really cool. And wow, did he smoke my time at 364 cycles. So what can Serbaldrig do? What did he do? So let's watch. So he splits that off. Splits off a bunch of stuff. Here it comes. So he has iodine there. He fuses a helium into the iodine. That skips element 54, which is xenon, which has no bonds, going to 55 cesium with one bond. So now it just has to fuse these guys all back into that, and output. So that's three solutions for this level, three completely different ways of solving it. If this level wasn't so hard, I think this would have been a good one for a public challenge to have everyone play, because this is really cool. I think that you could find a lot of interesting ways to solve this one. But let's get to the final tally. So MrBlarney set the mark at 364 cycles. Serbaldrig ends up with 335 cycles. Congratulations, Serbaldrig. You move on. This is Breeder Reactor by, this is Amro's solution. Turn uranium into plutonium. I really like this one. I think this is a fun challenge. So let's watch this first uranium atom. It goes into this reactor, where red grabs it, drops it out here, and then goes back to do something else. We'll come back to this reactor. This one uranium atom comes into this reactor, where, oh boy, does some incredible fission and fusion start happening. Now look at what he outputs here. Magnesium, sulfur, gadolinium. Okay, what's the point of this? So this here, now that this is done, this is all this reactor ever had to do. Create magnesium, sulfur, gadolinium. Send that one thing over to this reactor. The goal of this reactor is it wants to make helium out of this thing here. Now what happens is that sulfur, the gadolinium, and, well, germanium. The sulfur and the gadolinium it started off with are both both even powers of 2. That means when you split them down, it goes to helium with no lithium involved, no hydrogen involved. Now this is really cool. Red comes up, grabs the thing, bonds it if it can, then blue comes and splits it again if it grabs it. So he makes this huge crazy stick. Man, does this look weird, but there's a whole point to this, and it's ingenious. Now he gets to helium. Since it's helium, it broke the bond here, so blue did not bring it back up. Red can't bond it now, so it dropped. But then blue comes and splits it again. In this way, because everything here is a power of 2, things will either get rebonded, like this, or if it's helium, it gets outputted. This is genius. Look at how simple and efficient this way of creating helium is out of this stuff. That is amazing. And then now that he's got helium, it's really trivial just to input another uranium, fuse the helium in, and output plutonium. But this is where the action is. I love this. This is like Psuedodude, and this is amazing. But what happens when it gets to the magnesium? Magnesium is not a power of 2. Carbon. Well, you might have missed that. There's carbon in the output now. That's no good. It needs to be helium. But because of the way the math works, let's see. Carbon, 2 carbon is 12. 1 helium or 1 uranium is 92. So 92 minus 12 is 80. So 80 divided by 2, that means 40 heliums. Hey, 40 heliums. That's exactly what you need. The next thing, this is the very last plutonium that is needed for the output. There you go. It's at 39. Here's the last one. Blue would come in, and the next input would actually be the carbon and fuse into the uranium to make californium, I think. But it doesn't matter. This one solves at 430 cycles. So let's see what Orthogonalus can do with this. He has a 1-reactor solution, which... oh my! I love this. So Orthogonalus is kind of throwing in the towel, as you can kind of tell. He splits a uranium down until it becomes thorium. Red steals a helium. Thorium output, inputs a new uranium and fuses that, and moves plutonium out. So he's going to build up thorium waste into this pipe here. Obviously this is going to be very, very slow, and I don't think Orthogonalus really cares. But I love this. This got a laugh out of me. This isn't the days where you can get a participation point for submitting a solution. So, Amro wins by almost 2,000 cycles. Congratulations, Amro. So let's get into Jabor's solution for a laughable excuse, turning ammonium nitrate into nitrous oxide and water. Now, this is a challenge you don't really see very often because this is only assembly and disassembly reactors. That means in disassembly reactors like this you can only have unbonders and it only has one input. Assembly reactors can only have bond plus and it only has one output. So let's see what Jabor does. Starts off by just straight up splitting nitrate into the top and ammonium into the bottom. So let's follow the nitrate. Comes through, drops off oxygen and outputs it, and leaves a an NO here. Let's go back, see what ammonium does. Drops off a whole bunch of hydrogens here, outputs nitrogen down here. So this nitrogen goes, and with this NO, uses this method of creating a triple bonded nitrogen to create the nitrous oxide. I've always found that, yeah, triple bonding nitrogen if you have to is always a pain, so this is a really cool way to do this. Just have it go in a line and bond each way, create your nitrous oxide. These hydrogens meet up with these oxygens here to make water. Now this was the weirdest reactor. I was having quite a lot of problems trying to recreate Jabor's solution. It kept crashing. I really didn't understand what was going on here. It turns out the placement of these bonders here determines the order that these hydrogens get outputted in. So in this case it was top, this one here, then bottom for output. If you rearrange these bonders, it outputs a different way, which would cause this thing to collide and crash. Which was kind of confusing until I found that out. But there's that solution. Let's see how fast it gets. 937 cycles. Janderbuilt, almost exactly the same thing. Does a little bit of unbonding first here, because he can, I guess, to create nitrous oxide up top, and the ammonium ion on the bottom, with a hydrogen left over. But as I look at this, I see that he's got a bit of a backlog building up here. Did Jabor also have a backlog? No, Jabor seems to have pulling out the atoms pretty much as, or pulling out the inputs pretty much as close as they're coming. I'm seeing now these about halfway, they're starting to be a backlog built up. Let's see if that makes a difference. So his Janderbuilt solutions are pretty much exactly the same thing. 2 oxygens down here and NO up here. Gonna get this nitrogen from somewhere to make nitrous oxide. These oxygens, oh yeah. Ammonium ion gets hydrogens debonded, and oxygens come in and rebonded. It's almost exactly the same thing. This isn't really one of the most amazing challenges, and I have to admit that this was the last one I picked just because I needed something to fill out the 8th challenge. But I think it's still an interesting level to play. But he comes out at 999 cycles, not as fast, so congratulations Jabor for defeating Janderbuilt. Oh, this is neither here nor there, but I was watching Janderbuilt solution. I found a lot of ways to improve it a little bit. First of all, don't need that symbol. And you know what, since it takes 1 cycle anyway for that first input to come, you can get rid of that symbol there. But red will hit the start, so that means move that down there. And there, that works. That one was fine. That one was fine. This one's fine. I know there's a problem somewhere. Oh yeah. Doesn't need that bond either, because he inputs the beta. As soon as he inputs the beta, blue bonds it. At this pause here, blue will bond it again. Once red grabs, blue bonds it the 3rd time. So he didn't need that bond there. And since it takes a while for the first one to come, he doesn't need that arrow there either. So doing all this saves 4 symbols. No cycles, but 4 symbols there. Ah, here it is. I knew there was also another one. That can go there. But now red is a sync behind, so blue will have to start there and get rid of that. So it's exactly the same solution. I saved 2 more symbols. I always thought there might be a neat challenge to just take someone else's solution and rather than completely redesigning it, just tweak it a little bit to see if you can squeeze out some symbols. I think that would be a cool optimization challenge. But hope seeing that would give some people some ideas about not leaving extra symbols into a solution you don't need. Speaking about extra symbols into a solution you don't need, let's start off with the Haber-Bosch process. This is submitted by JavaJesus. So he does, what the problem of this solution is to try to sort nitrogen and hydrogen without using a sensor. So what he does is 1 bond here. Since there's only 1 bond between hydrogens, that hydrogen gets left. If this was nitrogen, it would still be connected. So that gets outputted, and that makes sense, hopefully. Eventually nitrogen, there. Nitrogen got debonded once, or twice because he timed it with blue. Drop, grab since it's still connected, and then he just needs that last one to unbond it. So with both of these guys working like this, he found a way to sort nitrogen up top and hydrogen up bottom. Then the next reactor is simple, just using sinks and inputs and bonds, exploiting bond priority, I think a little, or yeah, bond priority a little bit, to create ammonia. So this wasn't a terribly difficult challenge, but getting it down to a quick time is a little bit difficult. I played around with this in a little bit, and my fastest time was 825 cycles. JavaJesus, 821 cycles at 67 symbols. Mirroar, well, exactly the same thing. Using dropping a single hydrogens down here, drop grab thing, so that his nitrogens go up top, and then bonding the nitrogens together and again. Oh, excuse me. Been fighting a cold all week. Also sectoids, but that's a different story. Now, Mirroar did a slightly different thing in this reactor here. Somewhere around cycle 400, I think it was 400, there's a point right here where there's way more nitrogens than there are hydrogens. Now the input is heavily balanced towards hydrogen, but in this case, right here, around this cycle, there are way more hydrogens than you need, or way more nitrogens than you need. That's why the sinks are here. JavaJesus got around this problem by having a little bit of extra sinks down here. Mirroar did a thing where he has these extra bonds. That's what these extra blue bonds here are for. For example, if we move that bond out of the way, It still works a little bit, but then around the 400 cycle where there's the excess nitrogen, it doesn't work. So that's why he has all these extra bonds. Now note he has 67 symbols, exactly the same as JavaJesus. So this is going to come down to a cycle war. Who's faster? Trying to beat 821. 821 to 67. So, we have a complete tie between JavaJesus and Mirroar. It comes down really to time of submission, which is a little bit unfortunate, but I mean, I gotta find a way to pick one of these. I mean, they are exactly the same. JavaJesus submitted this on October 9th. Mirroar submitted this on October 11th. So JavaJesus, congratulations, you move on. So if only there was a way for Mirroar to save one cycle or one symbol out of this solution, he would have moved on. May that blue bond plus be a pox upon your head, Mirroar. That one symbol cost you from moving on. That's rough. I gotta say, wow. That is rough. One symbol in a cycle challenge made the difference. That's brutal. Sorry, buddy. But congratulations, JavaJesus. So now we're gonna move on to xenic acid. Taking the xenon out of xenic acid and just creating xenon output out of it. WildM emailed me a couple days ago saying he was surprised to learn that xenic acid was actually a real thing. It's not a chemical I made up. This really does exist. And people in the thread were saying that if instead of xenic acid it was just a xenon input here and a xenon output there, putting the pipeline straight into the output, it would take a little over 400 cycles for it to output, for the solution to finish. Because it takes 10 cycles to output 1, 10 times 40, 400 cycles. However, xenic acid has these hydrogens and oxygens left over, and nuclear reactors. So you can get way under 400 cycles if you fuse some of this garbage into more xenon. So let's see what added space did. Start off by getting rid of these hydroxyls over here, creating the oxygen and xenon down here. In this reactor, it takes these oxygens and xenons and outputs or drops off the oxygen as garbage and outputs xenons up here. So in this reactor, we're going to build up some oxygen garbage down here. These hydroxyls, they start getting fused together. So O and H add up to 9. 9 times 6 is xenon. So do this, fuse 6 of these together, you get a xenon. This is where this xenon comes from, and it gets kind of reintroduced into this reactor. So the output, instead of being in this one spot, there's an output of xenon here and down there. So that's a good way of reusing some of the garbage and having a bunch of oxygen waste here. Added space ends up with 347 cycles. Nethris is also going to have garbage. He made a little Pac-Man face out of his pipes. Now this is where it gets weird. What is here? Okay. Hydrogen, oxygen, oxygen, chlorine. Does that by fusing a bunch of stuff together. So xenon's up there. I'm more interested in seeing what the heck this thing is doing. So he takes this, fuses it a bunch together, creates a hobe here. So an oxygen and chlorine, another oxygen. Oh yeah, so manganese, that's, let's see, that's 3 oxygens and a hydrogen into there. Yeah, 3 oxygens and 1 hydrogen make manganese. He does a little cheaty thing by fusing and instantly bringing a new input to create molybdenum. Tin, oh, is it beryllium? So, wow, this is there's quite a lot of crazy fusion math here to get this xenon. And this garbage, hydrogen, oxygen, and beryllium hydrogen. But he still uses this garbage itself to fuse things. So this takes the xenon from out here that it created from fusing all this, outputs out here. This HOBEH starts all getting fused together. does he end up doing with this? Okay, from the beginning. So he fuses all that together and makes silicon. Fuses it all together, leaves a hydrogen as output. Fuse it all together. Oh, excuse me. Fuses it all together, zirconium. Fuses that. Xenon. So we create a whole bunch of xenon, and all of this, from all of this, there's 2 hydrogen wastes. And then in this reactor just takes 2 xenon outputs and from 2 different reactors and puts it out into 1. So as this works, 281 cycles, Nethris moves on. So the reason Nethris' solution is so much faster is basically because what he did with the waste. Look at all this oxygen waste that added space built up that could be turned into something. Nethris, how much waste does he have? Like 3 hydrogen atoms, 3 hydrogen molecules, that's it. That's 6 atomic units he didn't use. So that's why Nethris' solution is so much faster. Finally, clathrates and WildM solution. This looks a little bit complicated, but 217, that's a lot of symbols. WildM did a lot of work on this, so I'll try to do it justice to him. So he splits these silicon dioxide atoms in half. The ones that would have xenon get outputted up top. The ones that would have a krypton in there, I'll put it on the bottom. So let's follow the top one with the xenon. Split out the xenon, I'll put it down here. Split the silica in half, and I'll put that up here. So he's going to create all of his silica just from this half. So now the one with the krypton. Okay, what's happening here? Does a bunch of fusion... Ugh. This is confusing. Now let's wait until there's one with the krypton. So here's one with the krypton. Let's see what happens. Fuse stuff together, debond. So the krypton's no longer bonded. It can't be rebound. Rebound, sure. Take all this, fuse all that together. Sulfur, oxygen, titanium, and silicon. What the heck is he doing with that? This will have to start from the beginning. So silicon and titanium, fuse that together. That's krypton right there. The sulfur and the oxygen, that all came from oxygen. Fuse all those together, get cadmium, hafnium. Split hafnium in half, 2 kryptons. So there we go. So 3 oxygens make a chromium. 3 more oxygens make a cadmium. 3 more oxygens from that make hafnium. Split hafnium in half, you get krypton. So meanwhile, while that's going, this reactor is taking the xenon that came out of way at the beginning. From the xenon goes through to this reactor, from here down to here. So this guy takes krypton. Where does he get that krypton from? From the clathrates. So all of the xenon and the krypton that started off in the clathrates from the inputs go into this reactor. Then WildM does something I like to call noble gas math. Let's see here. If you krypton, if you split it in half, becomes argon. 1 argon plus 1 krypton equals a xenon. 4 argons is a hafnium. Right? Yeah. And then 2 split hafnium in half, that's a krypton. It's confusing until you actually do this yourself, but if you played the SpaceChem level that I got published in ResearchNet Nobility, you're gonna learn a lot about noble gas math, how the relationship between argon, krypton, and xenon works. So let's just watch through this one more time. So he gets krypton here. He's eventually gonna get a xenon. Xenon at some point. No, he's gonna solve and crash. So let's see what happens here. Somewhere around cycle 60. Okay, so we got a krypton up here, split it in half into argon. The xenon, fuse that, make hafnium. So xenon plus half a krypton to a hafnium. Do that again, get 2 hafniums. I'll put them both down here. So that was this reactor. So right in this pipe here, it's going to build up hafnium for a while, and it's not getting processed because that would be up here. This red is going through this crazy flip-flop counter. Once it's finally gets through that, it starts dealing with this hafnium backlog. So split, output krypton, split, output krypton, and this is kind of supercharging. By this point, silica's done. The limiting factor of this is how fast he makes krypton. So there's 4 more coming into the output, and that'll solve it. And then this point creates an input, another input, and crashes. You probably didn't see that, but this ended up at 241 cycles. On cycle 242, it crashes, because it's WildM. That's what he does. So let's look at LeschNyhan's solution. This starts off a little bit differently. Starts off by fusing an oxygen into a silicon. Silicon into that makes krypton. Then 3 oxygens get fused together to make chromium. So any of the krypton and xenon that started off in the inputs ends up on this top side. Downside gets krypton and chromium. From up here, this reactor takes this, and in case there's a krypton or xenon present, debonds it, sends it out here. So there's a xenon, gets outputted, splits this in half, and outputs a silica. So silica's done. For what he does with the noble gases, we should start at the beginning. So krypton and chromium, what happens to those? Well, this is the same noble gas math. Krypton moves straight over. Chromium, fuse 3 chromiums together, makes hafnium. Split that once, krypton. This reactor takes the krypton and the xenon that started out in the inputs inside the silica crystals, grabs the kryptons here, takes all the krypton, outputs it. The xenon gets sent out to a special reactor. This reactor does a kind of special thing with these xenons. Let's wait until I get one. Because I don't think this reactor ends up doing a full loop before the whole thing finishes. So split xenon into cobalt. Split cobalt once to silicon aluminum. Split aluminum once to get carbon. Carbon plus cobalt. Arsenic. Split as nitrogen. Fuse that in. Krypton. There we go. Fuse that together. Argon. Now that he's got argon, life's going to be a whole lot easier because you can just take xenon, fuse that into the argon, hafnium, split hafnium, and krypton. Well, I guess it does do a full cycle. But that's the solution by LeschNyhan, and you can already see it's not as fast as WildM's solution. At 383 cycles. Actually, on his submission he claimed that this was 382 cycles, but it doesn't matter, WildM's is faster. And why is that? Ooh, look at just kind of a backlog forming here in the inputs. Did that happen to WildM? Not really. WildM seems to have it timed perfectly so that there is no time spent in a backlog at the very beginning. So LeschNyhan, that's why. If you sped up his first reactor, they probably would have sped up his whole solution a lot faster. God damn it, WildM. Stop doing it. Oh, so that is everyone then. I would like to just say congratulations to Krackor, Psuedodude, Serbaldrig, Amro, Jabor, JavaJesus, Nethris, and WildM. You've moved on to the next round.